Hello, IBSL2. Today's topic is day 4, and it's volumes of revolution. Today we're going to be talking about volume, and here's a picture of what we're going to be talking about. I'm going to show you an animation here in a minute, but first just take a look at this picture and realize that the function is y equals 3x. So this line right here with a slope of 3 and an intercept of 0. And we'll look here at what the instructions are saying. When given a function of y equals f of x for a between x values between a and b, consider what would happen if the area under the curve was rotated around the x or the y axis. We're going to get something called the solid of revolution. And if this picture is a picture of y equals 3x being rotated around the x-axis, and you can see what shape would occur. Let's look at some animation in the Geo Sketchpad. This is a different function. This one is, our function is the square root of x, and our a values, they're not listed, but we can see them on our graph here. Would be at a is 2, and b in this example would be 9. And this animation is going to show you where it's going to be rotated. We're going to be finding the volume of this curve between values a and b around the x-axis. So I'm going to go ahead and push the revolve button and let you take a look at that. So that's a pretty cool thing. Hopefully you're enjoying that and realizing what that volume means. So this is if it was rotated around the x-axis. And again, this is our function, and it's the square root of x, and it's being rotated from values a to b around the x-axis. Let's look at another one where it's rotated around the y-axis so you can see how that looks. This time our function is 2 times the square root of x, and our a value is at 0 and our b is at 9 again. And this time it's going to rotate around the y-axis. So let's see what that would look like. So that's pretty neat, and you can see how the shape is obviously changed based on which axis you're going to revolve it around and what the function would look like. Again, this is being rotated around the y-axis, our function 2 times the square root of x, and our a values is 0 in this case and 9. If we drag the a value and make it from 2 to 9, you'll see that when it revolves, it's going to have a hole in the middle there as it's revolving because of our a values. So this is the shape being rotated around the y-axis. Couple other fun things we can do is look at a portion being rotated around, so just a smaller section being rotated around. Again, it's going to be rotating around the y-axis, and just one rectangle is going to be rotated. So that's pretty neat to see how that would look. And lastly, before we talk about the math of this, I want to show you one more. Actually, this one's pretty neat. See how our function is above and below the x-axis. So that's pretty fun to see how this volume, we have our f of x is this function, and our g of x is sine of x minus 1. So let's take a look at how this quadratic and the sine of x minus 1 revolve. So that's pretty neat, a whole different kind of shape. So today's topic is pretty fun. We're going to be talking about the volumes by revolution based on which axis we'll be revolving it and what our function looks like. So in our picture here, we were looking at y equals 3x as our function, rotating around the x-axis. In this graph, we again have our function of square root of x. I want you to go ahead in a minute here and pause the video, and what I want you to do is go ahead and draw one Riemann upper rectangle on your graph with the function of square root of x. And then I want you to think about what shape would this make when revolved. Think about some of the items that you just saw. Okay, as you thought about this shape, hopefully you drew your square root of x function correctly and then drew your upper rectangle correctly for this. I picked the whole section from 0 to 4. Yours might look a little different, but we would still have the same shape based on no matter how small that is, but the shape that we would revolve would be a cylinder. Let's take a look at this on the Geo Sketchpad. So I just drew changed my function to y equals 4 to represent the rectangle, and my a values are 0 to 4. And if I hit revolve, you can see our cylinder that will come if this shape, this rectangle, was revolved around the axis of the x-axis. Okay. So see how, depending on the shape and the curve that our function is, it will have a different shape. In this case, they asked us to draw a rectangle and revolve that around, so we have a cylinder. Let's take a look at what that means. If you're thinking about now this volume of the shape this is making, we're thinking about a volume of a cylinder. So remember all our volume formulas. For cylinder, we have the formula is volume equals pi r squared h for height. So know that all of these are in your formula packet. I just pulled up the formula packet that all of you have. Several of you have the blue copy still, and some have been picking up white copies. But notice where these are. These are in our prior learning formula, part of our formula packet. And here are all our volumes. So if you're looking for one while we're doing the homework, here's our ones that you may have forgotten over the years. Hopefully not. But anyways, they're all here if you need them. So our volume of a cylindrical disc would be volume of pi r squared h. So if we think of just the leftmost disc that has approximate volume, again I'll pull this up. So we are looking at the disc that is just at our a value here. If you just picture that again, the leftmost would be at your whatever your a is. I can change this to be a different a and a different b, but no matter what, your a will always be the leftmost disc. And this is the leftmost cylindrical disc. So if you think about that particular disc and you want to approximate the volume, you would use our volume equals pi times our function evaluate at a, whatever a they want us to evaluate, whatever our least value is, squared times delta x. Here, again, if you're looking at comparing the two formulas, so the volume of revolution is taken from our volume of a cylindrical disc. So here we have a pi r squared, is our function at the a value would be the r, the radius, and then we'd have to square it. And delta x, our change in x, is the height. Okay, I'll take a look at your graph again. Make sure that makes sense to you. Y is the radius. Our y value, everyone see why the radius is our y value here. And our change in x will be our delta x. And so the y value for this one here is at a. Okay, and you can see probably where I'm going. So if at the rightmost disk, it would be at b when you evaluate the y value of b. So here we would have this height for this disk at the function the y value of a, and here is at for the rightmost disk, our radius would be at the y value, this radius right here, our y value at b. So as you can see, as we look at our change of x as it approaches 0, so as we think of it as a limit, we will have our summation when x is a to when x is b. We would, same thing, we're going to be finding our integral. We can take the limit as the change in x approaches 0, and it is our integral from a to b of pi times our f of x squared delta x. This formula here is given to you in a little different format on the formula sheet, so let me show you how that looks. And let's pull this up some. So it's right underneath our area under a curve formula. They call it the volume of revolution about the x-axis from x equals a to x equals b. So they go ahead and write the y value here squared. So volume of a to b times pi y squared of delta x. But notice how our book writes it and how you'll be learning to use it will be plugging in our values to find our y. So let's see how this applies, and I'm going to go ahead and hide my work here. So our first step was to realize what the problem is, and our example is we're going to be using, this is the formula from your book, and which I prefer, like how they pull the constant pi out, and we're going to be using integration to find the volume of a solid generated when the line y equals x for the intervals between 1 and 4 is revolved around the x-axis. So anytime we are going to find the volume of a solid, we're going to be using this formula. So go ahead and pause the video and plug in your a and b value and your function. Okay, so you should have plugged in 1 for a and 4 for b, because that's our interval that they want us to find, and then x is our function. So you plug in x for f of x, and then that would be squared. Our next step is to find the antiderivative. So our antiderivative of x squared would be x cubed over 3, and then we're going to be evaluating that from 4 to 1. If we plug in 4, we have 4 cubed over 3, and then minus our plug-in of 1, which is 1 cubed over 3. And we'll just leave our pi out here. That just makes our math a little easier. So then that would simplify to 64 over 3 minus 1 over 3, which would be 63 over 3, which 63 divided by 3 is 21. So that makes our final answer of 21 times pi units cubed.